Let's try using the rate and concentration equation. That is, we know for a certain reaction involving a single reactant, the rate is actually equal to K times some power of the concentration of A. Let's try using this to actually find the time dependence of the concentration. So concentration versus time. That is, I want to figure out is that for a given reaction, how quickly does the concentration reaches a certain value. So let's start by taking the first order reaction case. So that is that we are still trying to use the reaction with a single reactant because that eases the computations a little bit. And for this, if this is a first order reaction, that means that the rate is equal to K times A to the power 1. This is a first order reaction. Now we know that rate is equal to this reaction rate is equal to the rate of decomposition of A, or in other words, this is actually equal to the negative derivative of the concentration of A with respect to time. And that is something we have covered in rate law, so let's use that. So we now have negative of dA over dt equals K times A. Now what you can do is you can take all the A terms to one side just to make the expression look better. So negative dA over A is equal to K times dt. And now this is in a form where you can integrate both sides. So let's do that. And the integration limits. So initially the time was equal to 0. The time was equal to 0. And the concentration was equal to a certain number. Let's take it to be A naught. And the time, the time that's variable, the time where we want to figure out the concentration, let's take it to be T, capital T. And the concentration that we want to figure out at capital T, let us take it to be A at capital T. Now what you can do is you can just integrate these equations, and we will use the following thing. So dx over x, the integral of 1 over x dx, is equal to ln x. And there is also a constant term, but since you are integrating with limits, this constant term just disappears. And also you also have a constant times dx, the integral of that is equal to K times X. So let's use that here. Now, one more thing, this negative sign here on the left hand side, this can be shifted over outside of the integral, and it still is a valid expression. So negative of the integral. Now we are all set to calculate this integral. So the negative sign, then in the brackets you have ln of x, but instead of x now you have the concentration of A. So natural log of the concentration of A between the limits A at t and A naught, A at time 0. And that is equal to kt between the limits capital T and 0. Now you can just plug in everything, so you will have negative, and then in the brackets you have natural log of A at t minus natural log of A at 0. Why? Because I just put in the limits, I evaluated the function, and I subtracted the two values. And similarly on this side, you have kt minus k times 0. And once you do it, once you evaluate it, once you simplify it further, you have negative of natural log of A at time t over A at time 0 equals kt. And since negative sign reverses the log, negative of log x is equal to log of 1 over x, you can write this as natural log of a naught over a at time t, and that is equal to k times t. And look how beautiful this expression is. This means that for a first order reaction, you can try to find out the exact concentration of the reactant once the reaction has started, given the time and the rate constant. A couple of things before we start using in the problem. There is something that's known as the half-life. Now what the half-life means is really simple. So basically you started with some concentration A naught of the reactant, and after some time, that's, let's say it to be T half, the half-life, this concentration reduces to being half of the original concentration. So that means that A at time T 1/2 is equal to 1/2 A naught. And you can use this to find the exact expression of T half, the half-life. So you would write then natural log of A naught, and instead of AT, you would now write half of A naught, and that is equal to K times T half. Instead of capital T now, you wrote T half. And here you can easily cancel the A naughts, and you would have natural log of 2. 1 over half is 2. Natural log of 2 is equal to K times T half. And that means that the half-life of a first order reaction is equal to natural log of 2 over the rate constant, and that's really nice. You could also have used an approximate value for the natural log of 2, and that is 0.693 over k. So 0.693 over k is again equal to the half-life, or you could have just used a natural log of 2. Now let's use whatever we have derived. Now an example. So let's take radioactive decay. So plutonium, some isotope of plutonium decomposes into certain products. You don't need to figure out what those products are. And it is said that, and in general, radioactive decay is a first order reaction. So you know that it has been experimentally found that the half-life of this reaction is equal to 6.58 into 10 to the power 3 years. So what that means is that you begin with 1 gram of plutonium, and after this many years, 6.58 into 10 to the power 3 years, you are left with half grams of plutonium. The other half gram has disintegrated into other substances. Now you want to find out how much plutonium remains after 100 years, after a century. That is, you want to know that if you put in half grams of plutonium, after 100 years, how many grams of plutonium still remains. So let's approach this problem. Now you have been given with just the half-life. So the only equation that you can use is this one right here. So you have K times T half is equal to the natural log of 2, and you know the value of T half. You know this value, and you need to find out K. So K is equal to natural log of 2 over 6.58 into 10 to the power 3 years. Whenever you're doing problems in chemical kinetics, just remember, especially with half-lives, just remember to include units as well. And now if you write this, you would have 0.693 over 6.58 times 10 to the power 3 years. That is equal to 1.05 into 10 to the power negative 4 years inverse, so 1 over years. And that is the rate constant. Now if you want to figure out what happens after 100 years, so you have now you have k, you have k, you have a naught, and let's just take a naught to be any arbitrary number, and you also have time is equal to 100 years. So then you would use this equation right here, so you have the natural log of a naught over a naught over a at 100 years is equal to k times, oops, let me do that in a different color, k times 100 years. So that's just, I have put in for t 100 years. And if you plug in the expression for k, if you plug in that expression, you have natural log of a naught over a at 100 years is equal to 1.05 into 10 to the power negative 4 times 100. And since this unit was in years inverse and this was in years, they just both cancel out. And thus, you would arrive at 1.05 into 10 to the power negative 2. And once you have this expression, the next thing you have to do is you need to do the inverse natural log on both sides. And that is equivalent to raising everything to the power of e being the irrational number which has an approximate value of 2.72. And if you do that, if you raise everything to the power of e, then you would arrive at, since e and natural log cancel each other, you then have a naught over a at 100 years is equal to 1.01. And then what you can do is you can also invert this expression, so you can take the reciprocal on both sides, so 1 over 1 over. So you then have a at 100 years over a naught is equal to 0.99, and that means that a at 100 years, the concentration of plutonium at 100 years is equal to 0.99 times the initial concentration. And that is pretty sad for the environment. So notice, if you start with 1 grams of plutonium and if you think that it will disintegrate, even after 1 century, even after 100 years, you are still left with 0.99 grams of that substance, and it will still continue to decay. However, if you have something like fermium, which is denoted by Fm, fermium 258. Fermium 258 has a half-life of 3.8 times 10 to the power negative 4 seconds. And its half-life is incredibly small, a fraction of a second. So that means that it will disintegrate really quickly. It will give off huge amounts of radiation, and it's not stable at all. However, something like uranium that is used in nuclear power plants, it has a half-life of about 4.5 into 10 to the power 9 years, and that's a relatively stable radioactive substance, and thus it's easier to deal with than other radioactive substances like fermium. So I hope that you have an idea of how first order reaction works, and the main takeaway here is this equation? Is this equation natural log of a naught over a is equal to kt, whatever time you have. The other takeaway is that you have the expression for half-life is equal to natural log of 2 over k. And finally, that radioactive decay is generally a first order reaction, and you can generalize this fact to other sorts of orders as well. See you in the next video.